Okay, yeah. Hi, everyone. So I'm Robert Stein, and I'm going to be talking about neutrino sources. And since I think I'm the only one talking about neutrinos today, I'm just going to remind everyone what neutrinos actually are. So we've known for over 100 years that the Earth is continuously bombarded by these things known as cosmic rays. Cosmic rays are not actually rays at all. They are charged particles. We know that actually they can have energies far exceeding what we could achieve, for example, on Earth with particle accelerators like the Large Hadron Collider at CERN. And because of that, that means that somewhere in the universe, there must be so-called cosmic accelerators that work like particle accelerators too, that are far more efficient. And it would be really nice if we could study them, because of course we're astronomers and we love to study extreme environments. But unfortunately, cosmic rays are, because they're charged, deflected by magnetic fields. And the universe is absolutely full of magnetic fields. And what that means is that if you imagine you have some distant cosmic ray source, it's emitting cosmic rays, and the cosmic rays don't travel on a straight line, but instead they follow a sort of windy, bendy, curvy pattern like this, until they eventually collide with the Earth's atmosphere. And what that means is even if you could detect a cosmic ray perfectly and say, I know this cosmic ray came from exactly over there, that basically doesn't do you any good, because the actual source of the cosmic rays might instead be over there or anywhere else in the sky. You'd have to know exactly what the magnetic fields of the universe look like before you can trace it back to its source. So this is a problem, but fortunately there is a solution, because nowadays we live in the era of multi-messenger astronomy. And when cosmic rays are produced, they can interact with ambient matter or photons and produce neutrinos. And neutrinos are electrically neutral particles that do not interact very much, which means that they travel in beautiful straight lines. They actually can pass through fields of dust or whatever else you have, and then eventually they arrive at Earth. And so the kind of key to understanding these cosmic accelerators is to study the neutrinos and work out where the neutrinos are coming from, because neutrinos can only come from cosmic accelerators. So that's the basic idea. And then to put it into practice, how do you actually detect a neutrino? And unfortunately, the things that make them so great as messengers also make them really, really hard to detect, because they are electrically neutral and they just don't interact very much. So the world's largest neutrino observatory is IceCube, located really directly at the geographic South Pole in Antarctica. So I want you to imagine if you're at the South Pole, what was done is basically you drill down through 2.5 kilometers of glacier ice, you lower a string into that hole. The string has PMTs distributed along it, so just photon detectors, and then you let the hole freeze up again. And you do that not just once, but 86 times in a kind of grid pattern. And then what you have is a grid of individual PMTs that can detect light in the ice. And this grid is 1 kilometer by 1 kilometer by 1 kilometer. So that's 1 cubic kilometer, hence the name IceCube. So IceCube is enormous, and it needs to be so big because then that's the only way to have even a chance of detecting 1 or 2 or 3 of these neutrinos. Just to give you a sense of scale, this little smudge here is supposed to represent the Eiffel Tower. The Eiffel Tower is large, but as you can see, IceCube is much, much larger than that even. And if we're lucky, what IceCube can do is you can imagine having a neutrino traveling through the Earth, for example, because neutrinos can do that, because again, they're capable of passing through matter. And maybe that friendly muon neutrino will interact. And again, if you're lucky, that muon neutrino will then produce a muon. And muons, unlike muon neutrinos, are charged particles, which means that as they travel through the ice, they'll be emitting light. And that's great because IceCube is a giant light detector, and so IceCube can detect a distribution of light. And what you might see in IceCube is something that looks like this. So each of these individual circles, there's 5,000, they represent one of the individual PMTs. And this pattern of light that's illustrated here is color-coded by arrival time. So red is early, green is in the middle, and blue is late. And so what you can already see, I think, by eye, is that you're seeing a particle that starts off here, slowly moves through the detector, and then eventually exits on this side. And you can imagine there are fancy reconstruction algorithms that are able to analyze this distribution of light and say this particle arrived from that direction on the sky. And that's actually amazing, because what that means is that you don't just have a neutrino detector, but you have a neutrino telescope. You're capable of detecting astrophysical particles and working out where they come from. And nowadays, IceCube is also very friendly. It's capable of detecting these automatically and sharing the positions in real time for astronomers around the world to point their telescope and hopefully identify where that neutrino came from. So right now, we know neutrinos exist. We know there are quite a few of them, but we don't really have a good idea of where most of them are coming from. So how do you go about figuring out where neutrinos come from? So I'd like to very briefly introduce the ZTF neutrino follow-up program. So the basic idea is that IceCube releases these neutrinos, and with ZTF, we basically observe the localizations of these neutrinos, and we analyze them in our mysterious data reduction pipeline here, and eventually hope to find electromagnetic counterparts. Actually, what we're doing is really not so mysterious at all. Once we remove things that aren't spatially and temporally coincident, and we remove things that are not likely to be neutrino sources, so things like stars and asteroids, we usually only left with a handful of potential transient counterparts. And then of these, we won't necessarily know what they are, but we can work it out because we can take spectroscopy to classify them. And at the end, that gives us a sample of all of the transients that are coincident with neutrinos. So what might be producing neutrinos? Well, here's kind of a hit list of key things that we'd be targeting. And the main sources are proposed are GRBs, or supernova with evidence of choked jets, supernova with evidence of CSM interaction, active galactic nuclei, and tidal destruction events. So let me just cut to the chase here and say, what have we found so far? So far, the most important result from our program is that we found, on one occasion, a tidal destruction event coincident with a high energy neutrino. And actually, we found not just one, but a second tidal disruption event too. So far, there aren't so many neutrino sources known, but with optical follow-up, we can find at least a couple, and so far we have two. So now that brings me to the key question of what I am doing here at the Keck Science Meeting. And I hope to convince you that I'm not here accidentally. So let's go back to this pipeline. And you may have noticed this very important step here in the middle. This is spectroscopically classifying the remaining objects. So a lot of this work is actually not super exciting. So there's a lot of GCNs that look a little something like this. I don't expect you to read this, but what this says is basically we did a follow-up, we found a transient counterpart, we took a spectrum of it with Keck, and we found out that it was a supernova 1A, and supernova 1A are not predicted to produce neutrinos. Therefore, we haven't discovered anything, and this is a rather boring upper limit. So there's an awful lot of this, but fortunately, I also have something slightly more exciting to discuss. So just within the last year, we were able to identify something new. So this is kind of an example of a source that we discovered in October of 2023. So this dotted line here, it indicates the detection time of the neutrino. We took ZTF optical data, and we immediately detected this very rapidly rising source that then started to decay very quickly. And for those of you who are maybe not so familiar with transient astronomy, this is extremely rare. It's very difficult to get a transient that can evolve really on the timescale of sort of 2 days to peak and then fading very quickly. So obviously the question becomes, what is this? And actually, just to give you a kind of illustration, there are really very few things that are capable of reproducing a light curve like this. So there are so-called luminous fast blue optical transients, which this object initially resembled very much. And there are also other very extreme supernova, but you can see that the source that we actually found was extremely luminous and extremely rapid. And this is a very this is not a very populated corner of parameter space. I mean, if you have to imagine that ZTF will detect thousands and thousands of transients every year, the number that look like this is just a handful, maybe 1, 2, 3, 4, 5. So what was this source that we found? Well, of course, we took a spectrum, and we took the spectrum with errors. That's why I'm here to tell you about it. And we were able to get a really nice classification. So this orange spectrum is our source. And the two populations I just outlined that kind of resembled this would be a luminous fast blue optical transient or a supernova of type 1Bn. And I think you can all see by eye what the orange one looks like. It looks much more like the brown than the pink. And so therefore, we're able to say that this is in fact a rapidly evolving supernova with CSM interaction. It is a type 1Bn supernova. So just to give you an explanation of what a 1Bn supernova is, because astronomers love their classification schemes for supernova, and you have all of the letters. What it basically means is that you have a core collapse supernova, but it doesn't have any hydrogen in it, which means that the outer layer of the hydrogen was stripped. And then you have the core collapse, and then you have a sort of dense helium-rich but hydrogen-poor circumstellar material around the supernova, and then basically the supernova shock collides with this and produces these lovely narrow lines that you see in the spectrum. So we didn't just get one spectrum with Keck, but actually we managed to get 3. So it's really cool to be able to see a source evolve in real time. So this is 3 spectra taken over the period of like 3 weeks, and they actually look really radically different. I mean, in the short space of time, they really the temperature of the continuum totally changes. You can see on the right that you have these really beautiful lines that evolve from having some absorption to then a very asymmetric with no absorption. And in general, why is this exciting? Well, this is the very first evidence we have. I mentioned that interacting supernovae are proposed as neutrino sources. People have looked a lot for this over the years, and there has never been a case of an interacting supernova found coincident with a high-energy neutrino until now. The spectrum that we took with Keck is essential because it proves that this is a supernova with CSM interaction in it, and that's exactly what you need for neutrino production. This is actually the first time I'm talking about this result. The paper is not on arXiv yet, but I hope it will be soon. But this is just maybe a reminder that Keck is very important for multi-messenger astronomy, and that doesn't just mean gravitational waves, but also for neutrinos, it's continuing to contribute to exciting results. So yeah, thank you very much. I think I'm out of time, so I'll just leave up this.